Another natural question about matrices of linear maps is this. Let's suppose you have a linear map T from V to W, and you've got two different bases of B and B prime, and two different bases of W, C and C prime. So you can take the matrix of T with respect to initial basis B and final basis C, and you can take the matrix of T with respect to initial basis B prime and final basis C prime. And the question is, what should be the relationship between those two matrices? They're certainly not going to be equal to in general, but there should be some kind of connection between them. That connection is described in the change of basis formula, which is the focus of this video. So here's the statement of the change of basis formula. You take a linear map T from V to W, you take B and B prime to be some bases of V, and they're not supposed to be related in any way, just two completely arbitrary bases of V, and two completely arbitrary bases C and C prime of W. Then the change of basis formula tells you that the matrix of T with respect to initial basis B prime and final basis C prime is equal to the matrix of T with respect to initial basis B and final basis C multiplied on the left by the matrix of the identity with respect to initial basis C and final basis C prime, and on the right by the matrix of the identity with respect to initial basis B prime and final basis B. The proof is going to use the composition formula from the previous video, so I'm going to write that out at the bottom here. The composition formula said that if you had linear maps, let's say from X to Y and from Y to Z, so let's say these linear maps are F and G, and if you had some bases which we'll call curly X, curly Y and curly Z of X, Y and Z respectively, then the matrix of G composed with F with respect to the initial basis curly X and final basis curly Z is equal to the matrix product of the matrix of G with respect to the initial basis curly Y and final basis curly Z, and the matrix of F with respect to the initial basis curly X and final basis curly Y. Okay, let's see how we can apply this composition formula in order to prove the change of basis formula. So first of all, we'll look at the matrix of T with respect to the initial basis B prime and final basis C prime. T is equal to the composition of T with the identity on V. Whenever you compose with the identity, it doesn't change the thing you composed the identity with. So we can simply do that. And then we can use the composition formula to get that this is equal to the matrix of T with respect to initial basis B and final basis C prime times the matrix of the identity with respect to the initial basis B prime and the final basis B. Next, we'll look at this part of the formula. That's the matrix of T with respect to the initial basis B and final basis C prime. And again, composing with the identity doesn't change anything, so we're free to replace T by the composition of T on the left by the identity in W. We can then use the composition formula, with the middle basis being C, to get that this is equal to the product of the identity on W, the matrix of the identity on W with respect to initial basis C and final basis C prime, and the matrix of T with respect to initial basis B and final basis C. Now we can just substitute the second of these into the first. So I'll show you what I mean here. We're going to take the matrix, the expression here, which is equal to the matrix of T with respect to initial basis B and final basis C prime, and we're going to substitute it there for this. And when we do that, what we get is exactly the change of basis formula. Okay, so that's the proof. Let's look at an example of using the change of basis formula. So we will take a linear map T from R squared to R squared, which is defined in the following way. T of vector xy is equal to the vector minus 16x plus 6y and then minus 45x plus 17y. We will take curly E to be the standard basis of R squared. You'll remember that what that means is that E1 is the matrix 1, 0, and E2 is the matrix 0, 1. And we'll take curly F to be the basis 2, 5, and then 1, 3 of R squared. You can check if you like that that really is a basis of R squared. It's linearly independent and it is a spanning sequence. In fact, of course, once you've checked that it's linearly independent, it must be a basis, because the subspace of R squared that it spanned would then have dimension 2. And since it's dimension 2, it must be all of R squared. Anyway, we'll call those things F1 and F2. And let's use the change of basis formula to find the matrix of T with respect to initial basis F and final basis F. So the special case of the change of basis formula in our situation would be that the matrix of T with respect to initial and final basis F would be the matrix of the identity with respect to initial basis E and final basis F times the matrix of T with respect to initial basis E and final basis E times the matrix of the identity with respect to initial basis F and final basis E. So we will work out the three things here on the right hand side and then multiply them together, and that will be the matrix on the left hand side. So let's work out the one in the middle first. Let's work out this thing, the matrix of T with respect to initial and final bases, the standard basis. So you'll remember that to do that, what we have to do is work out T of E1 and express that as a linear combination of E1 and E2, and that would tell us the first column of this matrix, and then do the same for T of E2, and that will be the second column. So T of E1 is T of 1, 0, which using the definition of T is minus 16 minus 45. So this stuff here will give us the first column of the matrix of T with respect to initial basis E and final basis E. Next, to find the second column, we look at T of E2, that's T of 0, 1, plugging into the formula for T, that's 6, 17. So this will be the second column of the matrix of T with respect to initial basis E and final basis E. The next thing we want to work out is the matrix of the identity with respect to initial basis F and final basis E. I'm choosing to do this one because it's easy. You will remember that when the final basis is a standard basis, it's very easy for us to work out these matrices. And the reason for that, well, just take a look at what's going to happen. If we want to make the matrix of the identity with respect to initial basis F and final basis E, we've got to do the identity to F1 and express that as a linear combination of E1 and E2. But the identity applied to F1 is just F1, which is 2, 5, and of course that's 2 times E1 plus 5 times E2. So straight away that just tells us that the first column of this matrix is 2, 5. And similarly, if we want the second column, well, that comes from applying the identity to F2 and expressing that as a linear combination of E1 and E2. But the identity applied to F2 is just F2 again. F2 is 1, 3, so this is E1 plus 3 E2, and this second column here is going to be just 1, 3. So we've worked out the whole of the matrix of the identity with respect to initial basis F and final basis, the standard basis E. So the only thing we haven't worked out on the left-hand side is the matrix of the identity with respect to initial basis E and final basis F. Now we could do that directly, but it's easier in this case to use the trick from last time, which told us that the matrix of the identity with respect to initial basis E and final basis F is the inverse of the matrix of the identity with respect to initial basis F and final basis E. Because our matrices are 2 by 2, it's super easy for us to work that out. We've got 2, 1, 5, 3 inverted, which if you use the formula for a 2 by 2 inverse is 3 minus 1 minus 5, 2. So we now know all of the three things on the right-hand side of our formula for the change of basis formula. So we're able to work out the matrix of T with respect to initial and final bases F by multiplying our three things together, the matrix of the identity with respect to initial basis F and final basis, initial basis E and final basis F, and then the matrix of T with respect to initial and final bases E, and then the matrix of the identity with respect to initial basis F and final basis E. when we multiply those three things together, this is what we get. So this is the matrix of T with respect to initial basis F and final basis F. But of course, a lot of calculation happened here. It's very easy to make mistakes when you do these amount of calculations. So it would be nice if there was an easy way to check our answer. So we can look at some of the things that this matrix predicts. We can look at what it means. And one of the things that it means is that first column of this matrix. So let's just highlight the first column here. This first column, what that's supposed to tell you is how to express T of F1 in terms of F1 and F2. So you'll remember we can label the rows by F1 and F2 and the columns by F1 and F2. And the first column is telling us how to express T of F1 in terms of F1 and F2. So what it's saying is that T of F1 is actually equal to minus F1. And the second column is telling you that T of F2 is equal to 0 F1 plus 2 F2. So we could check whether our calculation is correct by verifying whether or not T of F1 was equal to minus F1. That will give us a check. Won't tell us for sure because we need to check the other one if we want to know for sure. But if there was a mistake, it might show up when we verify that T of F1 is really minus F1. So let's do it. We're going to work out T of F1. F1 was 2, 5, so that's T of the vector 2, 5. And if you plug into the definition, you get this. If you work those things out, you get minus 2, minus 5, which really is minus, it's not minus F1, it's F2, is it? And that's not great. Let's get rid of this. What it really is minus F1. As you can see, F1 was 2, 5, and this was minus 2, minus 5, which is minus F1. So we're done. It looks like we haven't made any mistakes.